Hi everybody, hope your day is going really well. Our essential standard for today is I understand and can find critical points. This is where the first derivative is equal to 0 or undefined. I understand, can find, and can justify increasing, decreasing, constant behavior. These again are first derivative questions. Increasing meaning the first derivative is positive, decreasing meaning the first derivative is negative, and then constant is the first derivative is equal to 0. And this is the part we're actually doing today, is I understand, can find, and can justify extrema, giving a local argument for relative extrema and a global argument for absolute extrema. And we're going to learn a new argument for a relative extrema today. And so this is the second derivative test. Let's look at our particular diagrams up here before we delve into the specifics of the test. But I have a function where this function is curved up. It is concave up. The second derivative is positive. There is a point over here where the first derivative is equal to 0, meaning I have a tangent line, a horizontal tangent line. And if your function is curved up and you have a horizontal tangent line, if both of those things are true, you will end up with a relative minimum. Similarly, if your function is curved down, your second derivative is negative, and there is a point with a horizontal tangent line, that at that particular point there will be a relative maximum value. And this over here is our second derivative test. What this second derivative test says is as follows, and again this is a local extrema test justification. It says if the first derivative at a particular point is equal to 0, meaning the function has a horizontal tangent line, and if the second derivative is greater than 0, the function is curved up, then we're going to have a relative minimum. If the second derivative is less than 0, the function is curved down, then we're going to have a relative maximum. Unfortunately, this test can be inconclusive, and if the second derivative is equal to 0 at that particular point, this test is inconclusive, and then you have to go back and use the first derivative test. The reality of this particular test is this is not a test you want to use if you're given an analytic function. The first derivative test is conclusive. If you use the first derivative test, you will always get the right answer. It is never ambiguous. And so you would always want to use the first derivative test. Additionally, it takes typically extra work to find the second derivative. And so the second derivative test typically takes more work. And so if you have a choice, you're going to use the first derivative test. That said, when does this come into play? Sometimes you don't know what the values of the first derivative are on both sides of a particular point, but you do know the value of the second derivative at the particular point. This is the perfect way to use the second derivative test. And the second derivative test works super well if you don't know what happens on either side, but you do know the value of the first derivative and the second derivative at the point. And I probably talked about all these already, but let's just go through them again just in case. If information is known about the first derivative of a function on both sides of a point where f double prime of c is equal to 0, you would want to use the first derivative test as it is never inconclusive. The second derivative test should be used when both the first derivative is equal to 0 and the second derivative is known. If you're going to do an argument or a justification, you must refer to both the first and the second derivatives of the function of interest by name. We might say something like w of t has a relative minimum at t equals 4, since w prime of 4 is 0 and w double prime of 4 is greater than 0. That would be our justification. As I keep saying over and over again, avoid using the words increasing or decreasing in your justifications. Students who use these words do them typically incorrectly. We were analyzing signs, and so use the words 0, positive, negative in your justification because these words correspond to the analysis that you just performed. Some examples. They want us to find all the critical points for the function. They want us to determine if each critical point is a relative minimum, a relative maximum, or neither. They want us to justify our answers they want us to use the second derivative test unless it is inconclusive. Typically speaking, on tests, I will not force a particular test, whether it be a second derivative or first derivative test on you. You guys will have the choice, but there are ways to force a particular test where the first derivative test will not work and you will be forced to use the second derivative test. But if I leave it up to you, you're welcome to use either test because they both do work. Second derivative not always, but the first derivative test always. And so in order to use the second derivative test, we got to find the first derivative. And so let's go and do that. This first derivative of our function is going to be 6x to the 5th power. I need to find out when this particular first derivative is equal to 0. And if I do that, I get x is equal to 0. Now I need to find the value of the second derivative at this particular point. So I'm going to go and find my second derivative for the function. This is 30x to the 4th power. And then I got to find the value of the second derivative at the point that I have the horizontal tangent at. If I plug 0 into my second derivative, I get 0. Unfortunately, this test is inconclusive. It does not tell me whether I have a relative minimum or relative maximum. I have a horizontal tangent, but I do not know if this particular graph is curved up or curved down at this particular point. All I know is that the second derivative is equal to 0 at this particular point. And so I'm forced to go and do the first derivative test. I'm going to analyze my first derivative. I have a critical point at 0. And if I go and look at my function over here to analyze, if x is a negative number, you're going to get negative. If x is a positive number, you're going to get positive. And we are going to get a relative minimum. My function was going down, then my function went up. It was decreasing. I say f was decreasing, then f was increasing. And so we're going to give a justification. This over here has a relative minimum. And so we're going to say something like x equals 0 is a relative minimum since f prime changed from negative to positive. Don't stop there, because if you stop there, you will not get the correct answer. Just because f prime changed from negative to positive does not mean that x equals 0 is the relative minimum. It could be at some other point. Why is x equals 0 the relative minimum? Because f prime changed from negative to positive at x is equal to 0. The next one, in order to use the second derivative test, we got to go and find the first and the second derivatives. So let's get started with that. F prime of x is going to be this negative 15 x to the 4th power plus 15 x squared. When does this equal to 0? There is a negative 15 x squared that's in common. What's left over? X squared minus 1. This is going to be a negative 15 x squared. X plus 1, x minus 1 is equal to 0. And so when does this equal 0? This equals 0 when x is equal to 0, negative 1, or positive 1. And those are the points I want to evaluate with my second derivative once I find my second derivative. I'm going to go back to my first derivative up here, and I'm going to take the second derivative of that. And so what is my second derivative? This is going to be a negative 60 x cubed plus 30x. And now I want to find the value of the second derivative at each of those points. And so we're going to do f double prime of negative 1. If I plug in negative 1, what happens? Negative 1 cubed is going to be negative. Negative times negative 60 is going to be positive 60. And then we have the 30 times negative 1 is going to be negative 30. This over here is going to be 30. This is greater than 0. I have a horizontal tangent line, and my graph is curved up. If you have a horizontal tangent line and your graph is curved up, clearly this is a minimum. And so we're going to say that x equals negative 1 is a relative minimum since f prime of negative 1 is equal to 0, and f double prime of negative 1 is greater than 0. Horizontal tangent line curved up, that will be a relative minimum. So that over there is the first value. What about the middle value? And so we go and try to find f double prime of 0. This over here, again, when you're looking at this, these are these values over there. When we're looking at that over there, plugging in 0 is going to give us 0 plus 0. This is going to be 0. Our second derivative test is inconclusive. It does not tell us what the values are. We're going to have to go back and we're going to have to use the first derivative test on this particular item. And so if I want to analyze my first derivative, I have negative 1, I have 0, I have 1. I'd like to analyze, let's go and highlight this one. This is the easiest one to analyze. And so if I plug in a number like negative 2, the negative 15x squared will be negative, the x plus 1 will be negative, the x minus 1 will be negative, and if you have 3 negatives, you're going to get negative. If you plug in a number between negative 1 and 0, like negative a half, the negative 15x squared will be negative, the x plus 1 will be positive, the x minus 1 will be negative. We have 2 negatives, meaning it's going to be positive. If you pick a number between 0 and 1, like a half, the negative 15x squared is still negative, the x plus 1 is still positive, the x minus 1 is still negative. We have 2 negatives, this is going to be positive. And then if we pick a number that's bigger than 1, like 2, the x plus 1 and the x minus 1 will both be positive, but the negative 15x squared will be negative, and we have a single negative, and that's going to be negative. At x equals 0 over there, the function was basically going down, then it went up, it was going up, then it continued up, it was going up, and then it went down. At x equals 0, we do not get a relative minimum, nor do we get a relative maximum. This particular problem, they want us to determine if each critical point is neither or a relative min or relative max, and so we're going to have to justify that it's an either. X equals 0 is neither a relative minimum nor a relative maximum, since f prime does not change sign. Don't stop there. We still need the at x is equal to 0. Probably for that first box, I probably shouldn't have boxed everything. I probably should have just boxed the explanation. There was our explanation. The last one we got to do is the positive one. I don't have a whole lot of room, so I'm going to write it over here. But f double prime of positive 1 is going to be this negative 60 plus 30. This over here is going to be less than 0. And so if you look at that over there, is you have a horizontal tangent line, you have concave down, it's curved down, that is going to be a relative maximum. And so x is equal to 1 is a relative maximum. Since f prime of 1 is equal to 0 and f double prime of 1 is less than 0. That is our reason. Horizontal tangent line curved down. Relative max. Anyways, you guys get to try our next one. It says for the twice differential function f of x, a table of values is given for selected values of x. Is there a relative minimum, a relative maximum, an inflection point, or none of these at the point x equals 4? Justify your answer. So welcome back. What do we know about at x is equal to 4? We know that the y-coordinate is 12. We know that the first derivative is 0. That's a horizontal tangent line. And we know that the second derivative is 2, curved up. we know that we have a horizontal tangent line and it is curved up. Hey, what is that? That is going to be a relative minimum. There is a relative minimum at x is equal to 4 since f prime of 4 is equal to 0. That's the horizontal tangent line. And f double prime of 4 is greater than 0. That over there is the curved up. Now some of you guys say, well, I looked at this and 12 was the biggest value. How is that a relative minimum? Remember that when we have tables of values, we do not know what happens between the numbers. I do not know what happens between 2 and 4, and I do not know what happens between 4 and 6. Clearly, in this particular problem, somewhere between 2 and 4 it had to get bigger than 12. Somewhere between 4 and 6 it had to get bigger than 12 in order for 12 to be the minimum value. I don't have those values. I don't know what's going on there specifically, but I do know that there are values bigger than 12 in this particular function, because in order to get the relative minimum, you must have bigger values. Okay. Next one. This comes from the 2002 AP test, question number 5, part A. It was a no calculator question. Consider the differential equation dy dx equals. Let y equals f of x be the particular solution to the given differential equation for 1 less than x less than 5, such that the line y equals -2 is tangent to the graph of f. They want you to find the x-coordinate of the point of tangent C and determine whether f has a local maximum, a local minimum, or neither at this point, and they want us to justify our answer. And so we know that the line y equals -2 is tangent to the graph of f. And so we know that at a particular point, the slope over there would be 0. If you have this horizontal line, oops, sorry about that. If you have a horizontal line, y equals -2 is a horizontal line, then we would know that we're going to have a slope that's equal to 0. And so let's go find that particular point. And so we know that 3 minus x divided by y, that must equal 0. That line over there was horizontal, meaning the slope over there was 0. This particular equation is pretty easy to solve, and if we solve this, we're going to get x is equal to 3. And so the first part is they want us to find the x-coordinate at the point of tangency. Well, that x-coordinate must be 3. Then they want us to determine whether this has a local maximum, a local minimum, or neither. Well, I know I have a horizontal tangent. This particular function, since it has both x's and y's, is going to be difficult to analyze in terms of what's going on over here with the function. It'd be much easier to try to figure out what's going on with the second derivative, and maybe I can figure out if I have a concave up or a concave down, and I'll know what's going on. So let's go find our second derivative. D squared y dx squared. This is going to be a quotient rule. It is the denominator times the derivative of the numerator, which is going to be -1, minus the numerator times the derivative of the denominator, which is going to be dy dx, all over my denominator squared. I know what dy dx is. It is this 3 minus x over y. You don't really need to do that at this particular problem. I mean, you could plug it in and simplify. We just need to find the value of the second derivative at our point. So we're going to do that. We're going to do d squared y dx squared, and we're going to evaluate this at the point x equals 3, y equals -2. This is the point that we have for our tangent point. And so if I do that, the y value is -2. The x value is 3. And I get this 3 minus 3, which is going to be 0. It really doesn't matter what dy dx is, but I do know I had a horizontal tangent there. I do know that dy dx was 0 at that particular point. And this is all over the y squared, the -2 squared. My numerator ends up being +2. The denominator ends up being 4. This ends up being 1/2. I have a horizontal tangent line. I have curved up. I must have a local minimum. So f has a local minimum. At this point, since, why is it since? Since dy dx is equal to 0 and d squared y dx squared is greater than 0 at this point. But that's why we have a local minimum. Again, horizontal tangent line curved up. The next one, this one's your guys' turn. This comes from 2015. It was question 4. It was parts B and C. Give this one a shot, and then we'll go through it. The first part is they want us to find d squared y dx squared in terms of x and y, and then determine the concavity for all the solution curves for the given differential equation in quadrant 2. And so I got to find my second derivative. And so if I do that, I get this d squared y dx squared. The derivative of my first derivative is going to be 2 minus dy dx. They want me to write this in terms of x and y. They don't want me to write this in terms of dy dx, and so I need to replace the dy dx. Fortunately, I know what dy dx is equal to. It is this 2x minus y. This is going to be 2 minus 2x plus y. This over there is my second derivative. The second part is they want me to determine the concavity for all the solution curves given in quadrant 2. If you're over here in quadrant 2, which is over there, what do we know about the points in quadrants 2? The x values are going to be less than 0, and the y values are going to be greater than 0. If you plug in a negative number for x, that negative 2 times that negative number is going to be positive. And if you plug in a positive number for y, that number is going to be positive. And if you take 3 positive numbers and add them together, you're going to get a positive value. And since since the second derivative is positive, it is definitely going to be curved up. So we're going to say the solution curves in quadrant 2 are concave upwards. And then we're going to give our reason. What is our reason? Since what? Since d squared y dx squared is greater than 0, why? Why can we say that this over here is greater than 0? Since x is less than 0 and y is greater than 0 in quadrant 2. But that over there is our reason why we can say that it's concave up. Part C. Let y equals f of x be the particular solution to the differential equation with the initial condition f of 2 equals 4. Does f have a relative minimum, a relative maximum, or neither at x equals 2? And they want us to justify our answer. And so we know they want us to pick the point x equals 2. The point x equals 2 has a y coordinate of 4. And so we know we have the point 2 comma 4 as far as that goes. So let's go check this out. We have dy dx at the point 2 comma 4. What happens? If you plug that in, we're going to get 2 times 2 minus 4. We're going to get 0. We have a horizontal tangent. Second derivative, d squared y dx squared, evaluate at the point 2 comma 4 is going to give us what? Now we're using our second derivative, which is this part right over there. And if we use that part, we are going to get 2 minus 2 times 2 plus 4. This over here is going to be positive 2, which is definitely going to be greater than 0. I have a horizontal tangent. I have curved up. I must have a relative minimum. There is a relative minimum. at x equals 2, since what? Since dy dx equals 0 and d squared y dx squared is greater than 0 when x is equal to 2. The last thing for this video, this is some helpful homework advice. If it looks for some reason that it's going to be difficult to find the second derivative, just find the extrema with the first derivative test. The second derivative test is not meant to be always used. It is a good test. It is tested on the AP Calc exam. The way it shows up in our book is a little bit different than what it shows up on the exam, unfortunately. And sometimes the problems are very tedious trying to find the second derivative. Again, if the second derivative looks like it's going to take you more than a couple minutes to do, actually probably more than about 30 seconds to do, recommend doing just the first derivative test on that particular problem. If the second derivative is quick to do, say 30 seconds, go and try the second derivative test out. Anyways, if you have questions, please reach out to me and I'll do my best to help.